This presentation is delivered by the Stanford Center for Professional Development.
Okay, so welcome back, and let's continue our discussion on reinforcement learning algorithms. Outline for today, the first thing I want to do is actually talk a little bit about debugging reinforcement learning algorithms, and then I'll continue the technical discussion from last week on LQR, on linear quadratic regulation. In particular, I want to tell you about an algorithm called differential dynamic programming, which I think is actually a very effective optimal control / reinforcement learning algorithm for many problems. Then I'll talk about Kalmer filters and linear quadratic Gaussian control, LQG. Let's start with debugging RL algorithms. And can I switch to the laptop display, please? And so this was actually what I'm about to do here, this is actually a specific example that I had done earlier in this quarter, but that I promised to do again. So remember, what was it? Roughly halfway through the quarter, I'd given a lecture on debugging learning algorithms, right? This idea that very often you run a learning algorithm and it, maybe does roughly what you wanted, or maybe it doesn't do as well as you're hoping. Then what do you do next? And I talked about this idea that some of the really, really good people in machine learning, the people that really understand learning algorithms, they're really good at getting these things to work, very often what they're really good at is at figuring out why a learning algorithm is working or is not working. And that prevents them from doing things, for 6 months that someone else may be able to just look at it and say, gee, there was no point collecting more training data because your learning algorithm had high bias rather than high variance, so that 6 months you spent collecting more training data, I could have told you 6 months ago it was a waste of time, right? So these are the sorts of things that some of the people that are really good at machine learning, that really get machine learning, are very good at. Well, just flipping through my slides, these are, I won't actually talk about these, but these are exactly the same slides you saw last time. Well, shit, let's just skip ahead, I guess. So last time you saw just this discussion on, right, diagnostics for whether you might have a bias problem or a variance problem, or in other cases whether your optimization algorithm is converging or whether it's your problem optimization objective and so on. And we'll talk about that again. But the one example that I sort of promised to show again was actually a reinforcement learning example. But at that time, we hadn't talked about reinforcement learning yet. So I promised to do exactly the same example again. Right? So let's go for the example. The motivating example was robotic control. Let's say you write you want to design a controller for this helicopter. So this is a fairly typical way by which you might apply a machine learning algorithm or a set of machine learning algorithms to a control problem, right? Which is you might first build a simulator. So the control problem is you want to build a controller to make the helicopter hover in place, right? So the first thing you might do is build a simulator of the helicopter, and this just means model the state transition probabilities P subscript SA of the helicopter. And you can do this via many different ways. Maybe you can try reading a helicopter textbook and building a simulator based on what's known about aerodynamics of helicopters. It actually turns out that's very hard to do. Another thing you could do is collect data and maybe fit a linear model or maybe fit a nonlinear model to what the next state is as a function of current state and current action. Okay, so there's different ways of estimating the state transition probabilities. And so now you now have a simulator, and I'm showing a screenshot of our simulator we have at Stanford on the upper right there. Second thing you might do is then choose a reward function. So you might choose this sort of quadratic cost function, right? So the reward for being at the state S is going to be minus of the norm difference between the current state and some desired state. That would be one simple example of reward function. And this sort of quadratic reward function is what we've been using in the last lecture in LQR control, linear quadratic regulation control. And finally, you might run a reinforcement learning algorithm in simulation, meaning that you use your model of the dynamics to try to maximize that finite horizon sum of rewards. And when you do that, you get a policy out, which I'm going to call the policy pi subscript RL to denote the policy output by the reinforcement learning algorithm. Okay? And let's say you do this, and the resulting controller gives much worse performance than a human pilot that you hired to fly the helicopter for you. So how do you go about figuring out what to do next? Well, here are some of the things you might do, right? You might try to improve the simulator. So do exactly 3 steps. You might say, maybe I fit a linear model to my helicopter dynamics, but I think it's actually nonlinear. Or maybe you want to collect more training data so you can get a better estimate of the transition probabilities of a helicopter. Or maybe you want to fiddle with the features you use to model the dynamics of your helicopter. Right? Other things you might do, you might modify the reward function R if you think it's not just a quadratic function, maybe it's something else. I don't know. Or maybe you're unsatisfied with the reinforcement learning algorithm. Maybe you think the algorithm isn't quite doing the right thing. Or maybe you think you need to discretize the states more finely in order to apply your reinforcement learning algorithm. Or maybe you need to fiddle with the features you use in value function approximation or something. Okay? So these are 3 examples of things you might do. And again, quite often, if you choose the wrong one to work on, you can easily spend, actually this one, I don't want to say 6 months, you can easily spend a year or 2 working on the wrong thing. Hey, Dan, a favor, I'm sort of out of chalk. Could you wander around and help me get, thanks. So between those 3 things, I've copied the yellow box to the upper right of the slide. What can you do? So this is sort of reasoning we actually go through on the helicopter project often, and to decide what to work on. So let me just step through this example fairly slowly. So this is sort of reasoning you might go through. Suppose these 3 assumptions hold true, right? Suppose that the helicopter simulator is accurate. So let's suppose that you built an accurate model of the dynamics. And suppose that, so item 2 on the slide, suppose that the reinforcement learning algorithm correctly controls the helicopter in simulation so as to maximize that expected payoff, right? And suppose that maximizing the expected payoff corresponds to autonomous flight, right? If all of these 3 assumptions holds true, then that means that you would expect the learned controller pi subscript RL to fly well on the actual helicopter. Okay, so this is I'm sort of showing you the sorts of reasoning that I go through when I'm trying to come up with a set of diagnostics for this problem. So these are sort of diagnostics we actually use routinely on various robotics control problems. So pi subscript RL, right, we said it doesn't fly well on the actual helicopter. So the first diagnostic you might run is just check if it flies well in simulation. Right? So if it flies well in simulation but not in real life, then the problem is in the simulator. Right? Because the simulator predicts that your controller, the pi subscript RL, flies well, but it doesn't actually fly well in real life. And so if this holds true, then that suggests the problem is in the simulator. Is the question?
Just a question on the product. Did you have the real helicopter pilots try to fly on the simulator?
Yeah, is it actually finished off? Yeah, sorry, go on.
Did you have the real helicopter pilots try to fly on the simulator?
Do I try to have the real helicopter flying simulator?
The real helicopter pilots.
Oh, I see. Do we ask the helicopter pilot to fly in simulation? So yeah, it turns out one of the later diagnostics, you could do that. On our project, we don't do that very often. We informally ask the pilot, who's one of the best pilots in the world, Garrett Oku, to look at the simulator sometimes. We don't very often ask him to fly in the simulator. That answers the question. But let me actually go on and show you some of the other diagnostics that you might use then. Okay, second is let me use pi subscript human to denote the human control policy, right? Is pi subscript human is policy that however the human flies it. And so one thing you could do is look at the value of pi RL compared to the value of pi subscript human. Okay, so what this means really is look at how the helicopter looks like when it's flying under control of the pi subscript RL, and look at what the helicopter does when it's flying under the human pilot control, and evaluate and then sort of compute the sum of rewards, right, for your human pilot performance, and compute the sum of rewards for the learning controller performance, and see on, say, the real helicopter or that question, or you could do this on the real helicopter or in simulation actually, but you can see does the human obtain a higher or a lower sum of rewards on average than does the controller you just learned. Okay, and then the way you do this, you actually go and fly the helicopter and just measure the sum of rewards, right, on the actual sequence of states the helicopter flew through, right? And so if this condition holds true, right, where my mouse pointer is, if this condition holds true, where my mouse pointer is, if it holds true that pi subscript RL is less than pi subscript human, those of you watching online, not sure you can see this, but this is v pi subscript RL of S0 less than v pi subscript human of S0. But if this holds true, then that suggests that the problem is in the reinforcement learning algorithm, because the human has found a policy that attains a higher reward than does your reinforcement learning algorithm. So this shows that your reinforcement learning algorithm is not maximizing the sum of rewards. Right? And lastly, the last condition is this, the last test is this, if the inequality holds in the opposite direction. So if the reinforcement learning algorithm obtains a higher sum of rewards on average than does the human, but the reinforcement learning algorithm still flies worse than the human does, right? Then this suggests that the problem is in the cost function, is in the reward function, because the reinforcement learning algorithm is obtaining a higher sum of rewards than the human, but it still flies worse than the human. So that suggests that maximizing the sum of rewards does not correspond to very good autonomous flight. And so if this holds true, then the problem is in your reward function. Or in other words, the problem is in your optimization objective, and then rather than in the algorithm that's trying to maximize your optimization objective. And so you might change your optimization objective. In other words, you might change your reward function. Okay? So of course, this is just one example of how you might debug a reinforcement learning algorithm. And these particular set of diagnostics happen to apply only because we're fortunate enough to be able to an amazingly good human pilot who can fly a helicopter for us, right? And if you didn't have a very good pilot, then maybe some of these diagnostics won't apply and you have to come up with other ones. But I want to go through this again as an example of the sorts of diagnostics you use to debug a reinforcement learning algorithm. And the point of this example isn't so much that I want you to remember this specific set of diagnostics, right? The point of this is really for your own problem, be it supervised learning, unsupervised learning, reinforcement learning, whatever, you very often have to come up with your own diagnostics, your own debugging tools to figure out why an algorithm is working or why an algorithm isn't working. And this is one example of what we actually do on the helicopter. Okay? Questions about this? Yeah,
I was
Justin?
just curious how you collect like training data. Like in our homework, the pendulum fell over lots of times.
Right.
But how do you work that with an expensive helicopter?
Yeah, so I see, right. So on the helicopter, the way we collect data to estimate the state transition probabilities is we usually done lots of things, but to first approximation, the most basic version is if you ask a human pilot to just fly the helicopter around for you, and he's not going to crash it, so you can collect lots of data as it's being controlled by a human pilot. And as a side, it turns out, in data collection, there are sort of a few standard ways to collect data to let you, so a helicopter can do lots of things, and you don't want to collect data representing only one small part of the flight regime. And so concretely, what we often do is ask the pilot to carry out frequency sweeps. And what that means very informally is imagine that I'm holding a control stick, right, in my hand. Frequency sweeps are a process where you start off making very slow oscillations, and then you start taking your control stick and moving it back and forth faster and faster. So you sort of sweep out a range of frequencies ranging from very slow sinusoidal-like oscillations until you go faster and faster, and you're sort of jerking the control stick back and forth. So this is, oh, cool, thanks, man. So that's sort of one standard way that we use to collect data on various robotics. It may or may not apply to different robots or to different systems you work on. Yeah. And I should say, in reality, we do a lot of things. Sometimes we have controllers collect data autonomously too, but that's sort of another more complex algorithms. Anything else? Yeah, Sid?
In the first point, there could also be the case that the hardware is perhaps not mapping the actions similar to the simulator. So in robotics, it could be very common that you could have hardware bugs. Is there any specific method that is used to take care that hardware bugs don't cause problems?
Man, yeah, right. So saying, right, point one, it may not be that the simulator is accurate. It may be that the hardware is doing something strange with the controller. Is putting the controls through some action and through some strange transformation before it's actually sending this a helicopter. I don't know. Yeah, I've definitely seen that happen on some of the robots before. So maybe diagnostic one here is better thought of as deciding whether the simulator matches the actual hardware. I don't know. Yeah, that's another class of bugs to watch out for. If you suspect that's the case, I can't think of a good sort of diagnostic right now to confirm that. But again, before that'd be a good thing to try to come up with a diagnostic for, to see if there might be something wrong with the hardware. And I think these are by no means the definitive diagnostics or anything, right? This is sort of an example, but it'd be great if you come up with other diagnostics to check if the hardware is working properly. That'd be a great thing to do too. Cool. Okay, okay, last couple of questions as you move on.
You said the reward function was?
Oh, in this example, what I was just using a quadratic cost function. On the helicopter, we often use things that are much more complicated.
You have no way of knowing what is the desired pose.
Yeah, so you can futz with it, figure out where, ask the human pilot to hover in place and guess what S desired was. Again, these aren't cast in stone. You have to, yeah.
Yeah, I'm just wondering, these physics that are based learning problems, does it actually work in practice to use a physical theory model? Sort of physics itself, or do you just sort of do learning on the actual dynamics of the helicopter?
So do physics models work well, right? So the answer is it varies a lot from problem to problem. It turns out that the aerodynamics of helicopters, I think, aren't understood well enough that you can look at the quote specs of a helicopter and build a very good physics simulator. So on a helicopter, we actually learn the dynamics. I don't know how to build a physics model. For other problems, like if you actually have an inverted pendulum problem or something, there are many other problems for which the dynamics are much better understood and for which physics simulators work perfectly fine. It depends a lot. On some problems, physics simulators work great. On some, they probably aren't a good idea. Okay, cool. So let's switch back to the chalkboard, please. All right. So, okay. So let's go back to our discussion on LQR control, linear quadratic regulation control, and then I want to take that a little bit further and tell you about sort of one variation on LQR called differential dynamic programming. Just to recap, just remind you of what LQR, linear quadratic regulation control is. In the last lecture, I defined the finite horizon problem, where your goal is to maximize the sort of finite horizon sum of rewards, and there's no discounting anymore. And then we came up with this dynamic programming algorithm, right? Then we came up with this dynamic programming algorithm in the last lecture, where you compute v star of capital T, the optimal value function for the last time step. So in other words, what's the value if you start in the state S and you just get to take one action and then the clock runs out. Then with a dynamic programming algorithm that would repeatedly compute v star lowercase t in terms of v star t plus 1. So we compute v star capital T and then recurse backwards, right, and so on until we get down to v star 0, and then pi star was given by, as usual, the argmax of the thing we had in the definition of the value function. So last time, the specific example we saw of one specific example of the sort of finite horizon problem that we solved via DP was the LQR problem, where we work directly with continuous states and actions. And in the LQR problem, we had these linear dynamics where the state st plus 1 is a linear function of the previous state in action, and then plus this sort of Gaussian noise with Gaussian noise Wt, which has covariance sigma W. And I said briefly last time that one specific way to come up with these linear dynamics, right? One specific way to take a system and come up with a linear model for it is if you have some simulator, say, right? So in this cartoon, the vertical axis represents st plus 1, and the horizontal axis represents stat. So say you have a simulator. Right. Let's say a deterministic simulator, so a non-stochastic simulator that tells you what the next state is, st plus 1, as a function of previous state in action. I then said that you can choose a point around which to linearize your simulator, by which I mean that you choose a point and approximate the function f using a linear function that's tangent to the function f at that point. And so if you do that, you'd have st plus 1 equals So I wrote writing down on so many lines. But this would be the linearization approximation to the function f, where I've taken a linearization around the specific point s bar t, a bar t. Okay? And so you can take this and distill it down to a linear to a linear equation like that, right? Where the next state st plus 1 is now some linear function of the previous state st and at, and these matrices at and bt will depend on your choice of location around which to linearize this function. Okay. I said last time that this linearization approximation you sort of expect to be particularly good in the vicinity of s bar t, a bar t, because this linear function is a pretty good approximation to f, right? So in this little neighborhood there. And yes?
Is there an assumption that you're looking at dynamics only in a certain region of states, like the helicopter? Are you assuming hovering behavior is the same as attack behavior, or?
Yeah, right. So Right, so let me not call this an assumption. Let me just say that when I use this algorithm, when I choose to linearize this way, then my approximation will be particularly good in the vicinity here, and it may be less good elsewhere. And so when I actually talk about DDP, I actually make use of this property, which is why I was going over it now. Okay. But yeah, there is an intuition that you want to linearize near the vicinity of states that you expect your system to spend the most time. Right. So, okay, so this is how you might come up with a linear model. And if you do that, then you can, let's see. So for LQR, we also had this sort of quadratic reward function. Right? Where the matrices UT and VT are positive semi-definite, so the rewards are always negative, this minus sign. And then if you take exactly the dynamic programming algorithm that I've written down just now, then let's see. It turns out that the value function at every state, it turns out the value function for every time step will be a quadratic function of the state. It can be written like that. And so you initialize the dynamic programming algorithm as follows. And I'll just write this down, but there's actually just one property I want to point out later, but this equation is, well, somewhat big and hairy, but don't worry about most of its details. Let me just put that. Yes. Shoot, there's one more equation I want to fit in. Well, okay. So it turns out the value function is a quadratic function where v star t is this, and so you initialize the dynamic programming step with this. This phi and this psi gives you v capital T. And then you recurse backwards. So these two equations express, will give you v subscript t as a function of v t plus 1. Okay, so you recurse backwards for this dynamic programming. And the last thing, you get this on the same board, so. Let me. Sorry about the disorganized use of this board, just want this on the same place. And finally, the optimal policy, pi star of st, is given by some linear function of st. So LT here is a matrix where LT is equal to inverse times okay. And so when you do this, you now have the optimal policy, right? So just concretely, you run the dynamic programming algorithm to compute phi t and psi t for all values of t. And then you plug it in to compute the matrices LT, and now you know the optimal action to take from every state. Okay. So there's one very interesting property. These equations are a huge mess, right? You can rederive them yourself, but don't worry about the details. But there's just one specific property of this dynamic programming algorithm that's very interesting that I want to point out, which is the following. Notice that to compute the optimal policy, I need to compute these matrices LT. And notice that LT depends on, depends on A, it depends on B, it depends on V, and it depends on phi, but it doesn't depend on psi, right? Notice further that when I carry out my dynamic programming algorithm, my recursive definition for psi, well, it depends on, psi t. Right, psi t plus 1. Sorry. Okay. In order to carry out my dynamic programming algorithm, right, for psi t, I need to know what psi t plus 1 is. So psi t depends on these things. But in order to carry out the dynamic programming algorithm for phi t doesn't actually depend on psi t plus 1, right? And so, in other words, in order to compute phi t's, I don't need these psi's. And so if all I want is the phi's, I can actually omit this step of the dynamic programming algorithm and not bother to carry out the dynamic programming algorithm in terms of the phi's. And then having done my dynamic programming algorithm just for, excuse me, I misspoke. I can forget about the size and just do the dynamic programming updates for the phi matrices. And then having done my DP updates for phi t, I can then plug this into this formula to compute LT. Okay? And so, one way to think about it is you can, to be slightly more efficient, efficiency isn't really the issue, but if you want, you can actually forget about the phi t's. You actually don't need to compute that at all. Now, the other interesting property of this is that the matrix sigma W appears only in my DP update for the psi t's. It doesn't actually appear in my updates for the phi t's, right? And so you remember, my model was that ST plus 1 equals ATST plus BT AT plus WT, where these noise terms WT had covariance sigma W. And so the only place that appears, the covariance of the noise terms appears is in the psi t's, but I just said that I can do this entire programming algorithm without the psi t's. And so what this means is that you can actually find the optimal policy without knowing what the covariance of the noise terms are. Okay. So this is a very special property of LQR systems. And once you change anything, once you go away from a linear dynamical system, or once you change almost any aspect of this, if you go to discrete states or discrete actions or whatever, once you change almost any aspect of this problem, this property will no longer hold true. But this is a very special property of LQR systems, that the optimal policy does not actually depend on the noise magnitude of these noise terms. Okay? The only important property is that the noise term should have zero mean. And so there's this intuition that to compute the optimal policy, you can just ignore the noise terms. Right? It's as if so long as you know the expected value of your state ST plus 1, right, on average, ST plus 1 is ATST plus BTAT. Then it's as if you can ignore the noise in your next state ST plus 1, and the optimal policy doesn't change. Okay, so we'll actually come back to this in a minute. Later on, when we talk about Kalmer filters, we'll actually use this property of LQR systems. Just to point out, note that the value function does depend on the noise covariance. Right, the value function here does depend on psi t, and so the larger the noise in your system, the worse your value function. So this does depend on the noise, but it's the optimal policy that doesn't depend on the noise. I'll use this property later. Okay. So let's see how I do on time. Let's see. Right. Okay. So let's put this aside for now. What I want to do is what I want to do now is tell you about one specific way of applying LQR that's called differential dynamic programming. And as a motivating example, think of trying to control a system like a helicopter or a car or even a chemical plant with some continuous state. So maybe for the sake of thinking through this example, just imagine you're trying to control a helicopter. And let's say you have some simulator that estimates what the next state is as a function of the previous state in action. Right? And for this, let's say your model or your simulator is nonlinear and deterministic. Okay, so I said just now that the noise terms don't matter very much. So let's just work with deterministic simulator for now. But let's say f is nonlinear, and let's say there's some specific trajectory that you want a helicopter to follow. All right, so I want to talk about how to apply LQR to get a helicopter or a car or a chemical plant where your state variables may depend on the amounts of different chemicals, mixes of chemicals you have in different vats, right? Whatever. It's very easy to think about a helicopter. Let's say some trajectory you want a helicopter to follow. So here's what the differential dynamic programming does. First step is come up with what I'm going to call some nominal trajectory, right? And I'll call this S0, A0. Okay. And so one way to come up with this would be if you have some very bad controller. Let's say someone hacked up a controller for flying a helicopter. It's not a good controller at all. But you might then go ahead and fly the helicopter using a very bad, a very sloppy controller, and you get out some sequence of states and actions. Right? And so I'll just call this sequence of states and actions the nominal trajectory. Then I will linearize f around this nominal trajectory. Okay, so i.e., right, I'll use that same thing. So for time step t, I'll approximate st plus 1 as this linearization thing that we just saw. Times plus the other term. Okay. And then you distill this down to some ATST plus BTST, okay? And so this will actually be the first time that I'll make explicit use of the ability of LQR, or these finite horizon problems, to handle non-stationary dynamics. In particular, for this example, it will be important that AT and BT depend on time. Oh, excuse me. Okay. And so the intuition is that even if this is a pretty sloppy controller, even if you had a pretty bad controller come up with your original nominal trajectory, you still expect maybe, right? You'd expect your state in action at time t to be, maybe reasonably similar to what even a sloppy controller had done, right? So you want to fly a trajectory, maybe you want to make a 90-degree turn. Maybe you have a bad controller that does a pretty sloppy job, but at any given in time, you're still moving along this trajectory. And so this is really telling you where along, say, the 90-degree turn trajectory, just very roughly, where along the trajectory do you expect to be at any given time. And so let's linearize around that point. Okay. Then you would, having found a linear model, you run LQR to get the optimal policy for this specific linear model. And now you have a better policy. And the final thing you do is, boy, let me write this on a different board, I guess. The last step is you use a simulator or model to come up with a new nominal trajectory. So i.e. So now you take the controller you just learned and basically try flying your helicopter in your simulator. So you initialize the simulator to the initial state, I'll call it S bar 0. And then on every time step, you choose an action, which I'll call A bar T, using the controller pi T that you just learned using LQR. And then you simulate forward in time, right? Use the simulator, the function f, to tell you what the next state S bar T plus 1 will be when your previous state in action are S bar T, A bar T. And then you linearize around this new trajectory and repeat. Okay? So now you have a new nominal trajectory and you linearize your simulator around this new trajectory and then you repeat the whole procedure. I guess going back to step 2 of the algorithm. And this turns out to be a surprisingly effective procedure. And so the cartoon of what this algorithm may do is as follows. Let's say you want to make a 90-degree turn on a helicopter. Let's say you want helicopter to follow a trajectory like that. Start off with a very bad controller. Just hack up some controller, whatever. Have some way to come up with an initial nominal trajectory. Maybe your initial controller overshoots the turn, takes the turn wide. Right? But now you can use these points to linearize the simulator, to linearize even a very nonlinear simulator. And the idea is that maybe this state isn't such a bad approximation, that maybe a linearization approximation at the sequence of states will actually be reasonable because your helicopter won't exactly be on the states, but it'll be close to the sequence of states at every time step. And so after one iteration of DDP, if that's the target trajectory, maybe you get a little bit closer. And now you have an even better place around to linearize. And then after another iteration of DDP, you get closer and closer to find exactly the trajectory you wanted. Okay? So turns out DDP is a sort of turns out to be a form of a local search algorithm in which on each iteration you find a slightly better place to linearize, and so you end up with a slightly better controller and you repeat. And we actually do this. This is actually one of the things we do on the helicopter, and this works very well on many. This works surprisingly well. This works very well on many problems. Cool. I think I was actually going to show some helicopter videos, but in the interest of time, let me just defer that to the next lecture. I'll show you a bunch of cool helicopter things in the next lecture, but let me just check if there are questions about this before I move on. Yeah?
In the update, are you running through the entire trajectory?
In this step 4? Yes, yeah, right, yep. So I'm going to, let's have pick some finite horizon t, so I'm going to run through my entire trajectory in my simulator. So I end up with a new So I end up with a new nominal trajectory to linearize around. Right. Anything else? Yeah.
So does this method give you like a policy for performing like a certain action? Like you keep talking about like the 90-degree turn thing or something.
Right.
So is this for one one 90-degree turn or you know, can you use this for other general controller?
Yeah. So it turns out so this is used for let's see. Good way to think about this is if there's a specific trajectory that you want to follow. This could be on a car, on a helicopter, or it could be in a chemical plant, right? If there's some specific sequence of states you expect your system to go through over time, so that you actually want to linearize at different times. Excuse me. So that for the different times you want different linear approximations to your dynamics, right? So I actually started off with a stationary simulator, right? I mean, this function f, it may be the same function f for all time steps. But the point of DDP is that I may want to use different linearizations for different time steps. And so a lot of the inner loop of the algorithm is just coming up with better and better places around to linearize, where at different times I'll linearize around different points. Does that make sense? Cool. Okay, cool. So that was DDP. And I'll show examples of DDP results in the next lecture. So the last thing I wanted to do was talk about Kalman filters. And LQG control, stands for linear quadratic Gaussian control. And what I want to do is actually talk about a different type of MDP problem where we don't get to observe the state explicitly. Right? So far, in everything I've been talking about, I've been assuming that at every time step, you know what the state of the system is. And so you can compute a policy to some function of the state. Right? In LQR, we had that, the action we take is LT times ST, right? And so to compute the action, you need to know what the state is. What I want to do now is talk about a different type of problem where you don't get to observe the state explicitly. But in fact, before even talking about control, let me just talk about a different type of problem where, let me just forget about control for now and just look at some dynamical systems where you may not get to observe the state explicitly, and then only later we'll tie this back to controlling such systems. Okay? And as a concrete example, let's say, as sort of just an example to think about, we should imagine using a radar to track a helicopter, right? And so we may model a helicopter, and this would be an amazingly simplified model of a helicopter as some linear dynamical system. So next, say ST plus 1 equals AST plus WT, and we'll forget about controls for now, right? And we'll filter controls back in. And just for this example, I'm going to use an extremely simplified state, right, where my state is just a position and velocity in x and y directions. And so, you may choose an A matrix like this as a okay. As an extremely simple, as sort of an extremely simplified model of what the dynamics of like a planar object moving in 2D may look like. So just imagine that you're sitting in a station and you have a radar and you're tracking blips on your radar, and you want to estimate the position or the state of a helicopter as just as xy position and as xy velocity, and you have a very simple dynamical model of what a helicopter may do. So this matrix, this just says that xt plus 1 equals xt plus x dot t plus noise. And so that's this first equation. The second equation says that x dot t plus 1 equals 0.9 times x dot t plus noise. Okay, so this is an amazingly simplified model of what a flying vehicle may look like. Here's the more interesting part, which is that with if you're tracking a helicopter with some sensor, you won't get to observe the full state explicitly, but again, just for this cartoon example, let's say that we get to observe yt, which is CST plus VT, where the VTs are random variables, Gaussian random variables with, say, zero mean and Gaussian noise with covariance given by sigma v. Okay, so in this example, let's say that C is that, and so CST is equal to xy, right? If you take this state vector and multiply it by C, you just get xy. And so let's say you have a sensor, maybe a radar, maybe a vision system, I don't know, something that only gets to observe the position of a helicopter that you're trying to track. So here's a cartoon. Okay, so a helicopter may fly through some sequence of states. Let's say it flies through some smooth trajectory. Whatever, makes a slow turn. So the true state is four-dimensional, but I'm just drawing two dimensions, right? And so, maybe you have a camera sensor down here, or a radar, or whatever. And for this cartoon example, let's say the noise in your observations is larger in the vertical axis than the horizontal axis. And so what you get is actually one sample from the sequence of 5 Gaussians. And so you may observe the helicopter there at time set 1, observe it there at time set 2, observe it there at time 3, time 4, time 5. Okay? Right, so that's what you'll, that's the sequence of positions that your camera estimate gives you. And given these sorts of observations, can you estimate the actual state of the system? Okay, so these orange things, I guess, right? These orange things are your observations yt. And so to estimate the state of the helicopter every time, to estimate, say, the position of the helicopter at every time, clearly you don't want to just rely on the orange crosses because that's too noisy. And they also don't give you velocities, right? You only observe a subset of the state variables. So what can you do? So concretely, well, you don't actually ever get to observe the true positions, right? All you get to do is observe those orange crosses. I guess I should erase these ellipses if I can. Right, you get the idea. The question is, given, you know what I'm trying to do. Given just the orange crosses, can you get a good estimate of the state of the system at every time step? So it turns out that, so what you want to do is to estimate the distribution on the state given all the previous observations. Right? So given observations 1, 2, 3, 4, and 5, where is the helicopter currently? So it turns out that the random variables S0, S1 up to ST, and Y1 up to ST have a joint Gaussian distribution. So one thing you could do is construct a joint Gaussian distribution, can define a vector value random variable Z, S0, S1 up to ST, Y1 up to YT, right? And it turns out that Z will have some Gaussian distribution with some mean and some covariance matrix. And using the Gaussian marginalization and conditioning formulas, right? I think way back when we talked about factor analysis in this class, we talked about how to compute marginal distributions and conditional distributions of Gaussians. But using those formulas, you can actually compute this thing. You can compute, right? You can compute that conditional distribution. This will give a good estimate of the current state ST. Okay, but clearly this is a extremely computationally inefficient way to do so because these means and covariance matrices will grow linearly with the number of time steps. And so you're tracking a helicopter over tens of thousands of time steps. You end up with huge covariance matrices. And so this is a conceptually correct way, but just a computationally not reasonable way to perform this computation. What's my eraser? Okay. So instead, there's an algorithm called the Kalmer filter that allows you to organize your computations efficiently and do this. Just an aside, if you remember Dan's discussion section on HMMs, the Kalmer filter model turns out to actually be a hidden Markov model. These comments are only for those of you that attended Dan's discussion section. If not, then what I'm about to say may not make sense. But if you remember Dan's discussion section on hidden Markov model, it actually turns out that the Kalmer filter model, this linear dynamical system with observations, is actually an HMM problem where, let's see. Right. Fortunately, the notation is a bit different because Dan was drawing from, again, we're sort of clash of multiple research communities using these same ideas. So the notation that Dan used, I think, was developed in a different community that clashes a bit with the reinforcement learning community's notation. So in Dan's notation, in the HMM section, Z and X were used to denote the states in the observations. Today, I'm using S and X to denote the states in the observations. Okay, but right, but it turns out what I'm about to do turns out to be a hidden Markov model with continuous states rather than discrete states, which you saw in the discussion section. Okay. If you didn't attend that discussion section, then forget everything I just said in the last minute phrase. So here's the outline. So here's the outline of the Kalmer filter. It turns out that so it's a recursive algorithm. So it turns out that if I have computed P of ST given y1 up to yt, the Kalmer filter organizes its computations in two steps. The first step is called the predict step, where given P of ST, where you already have P of ST given y1 up to yt, and you compute what P of ST plus 1 given y1 up to yt is. And then the other step is called the update step, where given the second line, you compute this third line. Okay, where having taken into account only observations up to time t, you now incorporate the loss of the observations up to time t plus 1. So concretely, and let's see. In the predict step, it turns out that, and so what I'm going to do is actually just outline the main steps of the Kalmer filter. I won't actually, derive the algorithm and prove its correctness. It turns out that, working out the actual proof of what I'm about to derive is probably about as hard or maybe slightly easier than many of the homeworks you've done, right? So you've done some pretty amazingly hard homework, so you can work out the proof for yourselves. I just write out the main outlines and the conclusion of the algorithm. So the predict step turns out if ST given y1 up to yt, if that is given by that, then where so given st, having computed the distribution of st given y1 through yt, you can compute the distribution of st plus 1 given y1 through yt as Gaussian with this mean and this covariance, where you compute the mean and covariance using these two formulas. And just as a point of notation, right, I'm using st and yt to denote the true states and observations. And so the st is the unknown true state. Right? St is whatever state the system is in, and you actually don't know what st is because you don't get to observe this. And in contrast, I'm using these things like st given t, st plus 1 given t, sigma t given t, and so on. These things are the results of your computations. Right, so these things are actually things you compute. So I hope the notation is okay, but these st is the unknowable true state, right? Whereas these things, st plus 1 given t and so on, these are things that you compute inside your algorithm. Okay. So that was a predict step. Right, and then the update step, you find that, well, okay, and so that's the updates to the Kalmer filter. We compute this in terms of your st given y1 through yt. And so, after having performed the most recent Kalmer filter update, you find that right, your posterior distribution on the estimate of st plus 1, given all your observations so far, is that it's Gaussian with mean given by this and variance given by that. And so informally, this thing, st plus 1 given t plus 1, is our best estimate for st plus 1, right, given all the observations we've had up to that time. Okay? And again, the correctness of these equations, that the fact that I'm actually computing this mean and covariance of this conditional Gaussian distribution, I'll leave you to sort of prove that at home if you want. Okay. I'm actually going to put this together with LQR control in a second, but so before I do that, let me check if there are questions about this. Actually, let me erase the board while you take a look at that. Are there questions about Kalmer filters? Yep.
It's computationally less intensive than the other thing. You have to compute the some joint Gaussian distribution and then find the conditional.
Right. Okay. Yep. Cool. So how is this less computationally intensive than the original method I talked about? Right. So in the original method I talked about, well, let's switch back and forth. I said, let's construct Z, which was this huge Gaussian thing, right? And figure out what the mean and covariance matrix of Z is. And so, sigma will be like R. It'll be roughly, right, a T by T matrix. Right. This is actually order T by T. It's actually T times number of state variables plus number of observation variables by that. Right. So this is a huge matrix, and as the number of time steps increases, sigma will become bigger and bigger, and so the conditional and marginalization operations require things like computing the inverse of T or subsets of T, and so the naive way of doing this will cost on the order of T cubed computation if you do things naively, right? Because inverting like a T by T matrix costs on the order of T cubed, roughly. In contrast, the Kalmer filter algorithm, I guess over here I just have the update step. On the other board I had the predict step. But you can carry out the computation on both of these lines in essentially constant time. And so on every time step you perform these Kalmer filter updates. And so if every time you get one more observation, you perform one more Kalmer filter update. And the computation of that doesn't depend on, it's order one time for every time step. So the amount of stuff you need to keep around in memory doesn't grow linearly with the number of time steps you've seen. Okay? Because actually, I think I just realized why. So this is the way we actually run Kalmer filters, which is initially I have just my first observation, and so I would then compute P of S1 given Y1, right? And now I know where I think my helicopter is at time step 1. Having computed this, there may be some time passes, like a second passes, and then I'll get another observation. And what I'll do is I'll combine these two together to get P of S2 given Y1 and Y2, right? And then maybe another second passes in time, and I get another observation. So my helicopters move a little bit more because another second has passed, and I get another observation. And what I do is I combine these two to compute P of S3 given Y1, Y2, Y3. And it turns out that in order to compute this, I don't need to remember any of these earlier observations. Okay? So this is how you actually run it in real time, say. Okay, cool. So, running out of time. But the last thing I want to do is actually put these things together. So putting it together, putting Kalman filters together with LQR control, you get an algorithm called LQG control, which stands for linear quadratic Gaussian. But in this type of control problem, we have a linear dynamical system. So I'm now adding actions back in, right? So now B times AT. And okay. So in an LQG problem, or linear quadratic Gaussian problem, I have a linear dynamical system that I want to control. And I don't get to observe the states directly. I only get to observe these variables yt. Okay? So I only get noisy observations of the actual state. So it turns out that you can solve an LQG control problem as follows. At every time step, we'll use a Kalman filter to estimate the state. Right? So concretely, let's say you know the initial state, then you initialize this to be right, that. If you know that the initial state is some state S0, you initialize that to S0 and that, or whatever. Right, and this is just, well, if you don't know the initial state exactly, then this is just the mean of your initial state estimate, and that would be your covariance of your initial state estimate. So you just initialize your Kalman filter this way. And then you use the Kalman filter on every step to estimate what the state is. So here's the predict step. Right. Previously, we had st plus 1 given t equals, right, and so on. So this is a predict step, and then you have an update step, same as before. The one change I'm going to make to the predict step is now I'm going to take this into account as well. This is just saying, suppose my previous state was st given t. What do I think my next state, st plus 1 given t, will be, given no other observations? And the answer is, it's really just this equation, right? ast given t plus bat. And then, so this takes care of sort of the observations. And then the other thing you do is compute LTs using LQR, right? Assuming then the other thing you do is you just look at the linear dynamical systems and forget about the observations for now, and compute the optimal policy. Right. Previously, we had that you would choose actions AT equals to LT times ST, right? So the optimal policy, we said, was this, these matrices LT times ST. So in the other part of this problem, you would use LQR to compute these matrices LT, ignoring the fact that you don't actually observe the state. And the very final step of LQR control is that, well, when you're actually flying a helicopter, when you're actually doing whatever you're doing, you can't actually plug in the actual state, because in an LQG problem, you don't get to observe the state exactly. And so what you do when you actually execute the policy is you choose the action according to your best estimate of the state. Okay? So in other words, you don't know what ST is, but your best estimate of the state at any time is this S of t given t. So you just plug this in and take LT times your best estimate of the state, and then you go ahead and execute the action AT on your system, on your helicopter or whatever. Okay? And it turns out that for this specific class of problems, this is actually the optimal procedure. This will actually cause you to act optimally in your LQG problem. And this is intuition that earlier I said in LQR problem, it's almost as if the noise doesn't matter. In the pure LQR problem, the WT terms don't matter. It's as if you could ignore the noise. So it turns out that by elaborating that proof, which I'm not going to do, you're welcome to prove for yourself at home, that intuition means that you can actually ignore the noise in your observations as well. The ST given T is sort of your best estimate. So it's as if, it's as if your true state ST is equal to ST given T plus noise. And so in LQG control, what we're going to do is ignore the noise and just plug in this ST given T. And this turns out to be the optimal thing to do. I should say this turns out to be a very special case of a problem where you can ignore the noise and still act optimally. And this property, this is actually something called the separation principle, where you can design an algorithm for estimate the states and design an algorithm for controlling your system, and sort of just glom the two together, and that turns out to be optimal. This is a very unusual property, and it pretty much holds true only for LQG. It doesn't hold true for many systems. And once you change anything, once it's nonlinear, some other noise, once it's nonlinear, once you change almost anything in this problem, this will no longer hold true. You can just estimate the states and plug that into a controller that was designed assuming you could observe the states fully. But once you change almost anything, this will no longer turn out to be optimal. But for the LQG problem specifically, it's kind of convenient that you can do this. Just one quick question, then I should close.
So A and B are known?
Yes, yeah, and everything I'm assuming, in everything I described, I'm assuming you've already learned A and B or something. So yeah, right. Okay, sorry about running a bit late. Let's close for today, and next time I'll talk a bit more about these partially observed problems.